Okay, so what we're going to talk today about? We're going to talk about stacks again, then we will talk a little bit about queues, and finally we will talk about heaps today. I will try to stick to the plan, and unfortunately I'm not very good prepared for this lecture, so excuse me in advance. It will happen because like I prepared it for the last time, but like there is already 1 week past, so I could forget something. So let's continue with the stack. What's the next problem? So we talked last time about the problems about brackets and the problem about what was it? About like how to calculate maximum on the stack. So today we will talk about a little bit more interesting problem. So you have a line of n people, and we know their height of each person. So there is a person there, yeah, so this is their my best drawing skills. And we want for each person to understand how many people on the left he can see. So on the left, so he looks like I don't know how to exactly say this problem to be more precise. So the person can see another person if there is nobody with the higher height between them. So for example, this person can see this person because he has much higher height than everybody here. But at the same time, this guy cannot see this guy because there is a guy in the middle who has higher height. So, and the question is, how many people each person can see on the left to itself? So I again give you some time to think about this. Like, is the problem clear? Like, that's the first question. Okay, good. So you have to solve it using the stack. So like, let's think a little bit like for 1 or 2 minutes and then try to come up with a solution.
Shall we make a code, or can we solve it analytically?
No, analytically. No. I'm just like as usual, like right now.
Like with words, right?
Yeah, sure.
Okay, so maybe just make it via talking. So like we first look at the left and we find a person and put it in a stack. So it would be like the third person in the array. May I continue, or somebody needs some time?
I would like to tell at first that you should do this in off n time, where n is the total number of people there.
Okay.
Sorry, I didn't specify this in the first place, like I thought.
So may I continue?
Yeah, sure.
Okay, so then we go to further step and we pick the second guy in the row, and we pick the guy from the stack, which is basically the third guy in the array, and we like compare them, and as soon as the second one is less has the less high than the third one, we do not put him in a stack, and we continue, and that's the first guy, and we look in the stack again, and it is our third guy there, and as soon as the first guy's high is bigger, we put him in a stack, and we make like +1. So at the end we have 2.
So you're going from right to left,
Yeah.
and adding them to the stack. You should.
Yeah.
Yeah, it's approximately what I wanted to see. The thing is that you should calculate this for all persons in linear time. Okay. So you have to count for each person the number of people he can see on the left in linear time. It is solved approximately as you just told me, Maria, but like a little bit different, a little bit. So any ideas on how to do this in linear time for everybody?
Okay, we can create an array. I'm talking and thinking at the same time.
Okay.
We can create an array, and the index of this array would be like the index of a person, and we could make the +1 operation if he can see the person. So we can storage this kind of data in this array. And as soon as we need to use stack, we can go from the same direction as I mentioned before. And if a person we are talking about can see is has less high, then we add +1 to his index, but we do not add the same thing for another person, like that, still using the stack.
It's almost right. almost right, but like not I don't understand why do you still have linear time complexity of the algorithm.
I have a feeling that it is somehow similar to when we try to find the maximum of the stack, like this structure of making two data types, etc.
Okay, anybody else has an idea on how to improve what Maria discussed right now? Okay, so then I will explain how to do that. So you go from the left to the right, and you maintain the people that you can see at any moment in time on the left. So at start we have this, the first guy on the stack. Then you add the small guy there. And when you add this guy to the stack, you just make the number of people in the stack. So here is stack. Then we take the third person and look on everybody who is on the stack, how many of them. You can see that there are 2 of them, so you take for answer 2. And then you add our person to the stack. When you add this person to the stack, who is not visible anymore?
The second guy.
Yeah, the second guy isn't visible anymore, so we just simply withdraw from the stack all the guys that are smaller than the one we are adding right now. So we take this guy out and put their third guy here. And then you add the fourth guy. And again, you see that the number of persons in the stack is 2, so you add to the answer is 2. However, this guy is still higher than the guy that is seen here. So we should withdraw all the guys who are smaller than our fourth guy. So this is the third guy. You throw him out and add our fourth guy here. So the algorithm is simple. You just go from left to right. When adding a person, you just take the number of persons currently in the stack. So like every time the persons in the stack kind of shows the decreasing sequence of guys. So like their height are decreasing from left to the right. And when you add the new guy to the stack, you withdraw all the guys that are smaller than him. So nobody can see them. That is all. So why it is working in linear time? It works in linear time because you take one person each time, and each person can be added to their stack once and removed from the stack once. So in total you have constant time per each person, so there is O(n) time in total. Questions here?
No, it's quite simple.
Yeah, it's quite simple though. Yeah, and Marie, you were almost right, almost, but like not exactly. Okay, good. That's what I didn't have time to finish last lecture. So like now we finish with the stacks for a little bit of time. Then we will talk about queues. So what is Q? Q is FIFO order. So first in, first out. So you have two operations, add and get. Add adds the person there, and get returns their latest person who is standing in the queue. So like this is simply the queue there. So here is how you remove the guy from the front and add the guy to the end. So the first question is how to implement it. I didn't talk a little bit about stack right now. There is some issues with the stack that I will cover to the end of this lecture, the kind of theoretical problems. But for the queue, like in the stack, it was pretty simple. You, for example, allocate very huge array and add the guys to the end where top is. However, with queues, it's not very simple to do because you are removing the guys from the front and add the guys to the bottom. So you cannot create the huge array if you have lots of operations, but you know that the queue can be of fixed length, because like typically how will you implement? You will have like two counters, like add will be Q of R equals to X R plus plus, and get will be L plus plus return Q of L minus 1. So this you would how to implement there. The Q. However, this L and R are always increasing. So how to deal with that? Suppose that you know that the highest length of the queue is L in total. So you create an array L of size L. And when you add an element to the queue, you just store the queue in this array. Like for example, it is like this right now. But when R is coming to the end, it just doesn't go forward to the right, but otherwise it comes to the beginning of the array. So like the queue currently right now is presented as like this. So starting from the left, ending with the right. So we just take here we just take R equals R modulo L. And here, like similar with L here. So you just make a circular queue out there.
Sorry, is it in R? Oh, sorry. Is it in Java as well? Because I've heard this circular data structures can be implemented only in several languages, like Python, for example.
Yeah, you can implement this in this Python.
Okay.
Why you cannot? Why do you think so?
No, about Java. Like, is it possible in Java as well?
What exactly do you think is not possible in Java?
No, I just asked if it is possible in Java as well.
Like,
because I've heard otherwise.
That you cannot allocate an array and take modulo length? Sorry, I'm a little bit confused. Why? Who told you that it's impossible to implement?
I think it was a rumor. Okay, thank you.
Okay. I mean, you just like when you add L, you also like add here, like you just move the counter, and when you come to the end, you just have L here, and then you move. Yeah, to be honest, R is always on the next, so like R points to the first element that doesn't belong to the queue. Sorry. Left is always the head of the queue, but R is a little bit to the right, to their tail. So yeah, you can implement this in any language, I think, that you want, almost at any language. Okay, so let us think in that we understand how to write it using the counters. Are there any questions right now? Like, is something unclear with their queue?
No.
Okay, good. So, the question is, I add the elements to the queue. So again, as almost as with maximum. So like we have three operations that queue should be able to respond. So we have add, get, and tell me the sum of elements in the queue. So like these are three operations that are going to ask our black box data structure that we have to implement. Like as in the previous, maximum can be requested multiple times. Sum also is requested multiple times.
So we need the additional variable where sum is and every time when we add new value to the queue, we also sum it to the variable sum, and when we call the sum, we get the value of the sum variable.
Yeah, that's it. Was Kostya, right?
Yes.
Okay, so like I'm just keeping in mind who is answering. Yeah, exactly. You just store an additional variable, and when you make add, then you add to this variable sum, and then you get you retrieve it. Okay, so let's make this problem a little bit more complicated. We want not sum, but maximum. I will give you a short amount of time because I'm not sure that you will be able to come up with a solution here. So you can think a little bit, but like don't stress too much. That's kind of complicated algorithm.
Then we can use one queue and a stack, or two queues.
How?
We will one use as a usual queue, and the second one will maintain the same number of elements, but they will be of the current max. And then if we move queue, we also I think pop from the stack. So the top of the stack will be maximum of the queue that we are moving, and the both will be the same length. Yeah, and current it's maintaining this max.
And how do you pop from, when do you pop from the queue? From the stack?
When I get from the queue.
When you get out of the queue, but if your element lies in the middle of the stack?
If we get from the queue, it is also a maximum because we don't need to pop from the stack, like the maximum element.
No. When we add to the queue, we always, even if it's we already know the maximum, we just add the maximum anyway. So in the stack, we can have a repeating sequence of maximum. So we just pop anything we want, and it will just move accordingly. So it can repeat.
Yeah, the problem that I'm not sure that I understand how to do we deal with add 3, add 2, add 1, then okay, then add 2, and then you make pop 3 times. So you put 3 here on the stack when you add, then you try to put 2, but 2 is less than 3. So you don't put on the stack as far as I understand.
So yeah.
Yeah, so like when you pop 3, you will never get 2 as the answer. So yeah, but like, okay, do not frustrate too much. This is like impossible to come up in like 2 minutes, but you were kind of close. We indeed have not 2 queues, but 2 stacks for that. So right now we will implement how to implement queue using 2 stacks. So we have 2 stacks, and when we add an element, so we start adding them in the second stack. When the get operation comes, we do the following. We look, oh, is there something in the stack, in the first stack? If it's not, then we take everything from the second stack and put them in the first stack. So we just take x3 out, put it here. Then we take x2 out, put it here. And then we take x1 out and put it here. You can see that the first element comes there on the top of the stack. So the next time when we ask get, we will get the first element that were inserted. So then you got x1, x2, x3, and again you just continue adding the elements to the second step. So like it can be here like x4, x5, x6. But when get see the first stack and there is something in there, it just retrieves this element from the stack. Like it retrieves x1, then it retrieves x2, then it retrieves x3. And then when he tries to retrieve again, the stack is empty, and it takes all the elements from the second stack and move them to the first stack.
Could you please show an example?
This was not example enough?
No, it wasn't, unfortunately.
It means it is not clear what's happening.
But we need additional operation to move every element from one stack to another. Is it a good solution?
So again, like how get operation works. Get operation, if like that there F stack and second stack. if f.empty, then while let me write it there. If f empty, then while not s dot empty, we take f dot push s dot pop. And then we just return f dot pop. What about add? In the add, we just add element to the second stack, s dot push of x. So that's it. That's the whole algorithm. So if the first stack is empty, then take everything from the second stack and put it there. And in all the cases, just pop the first element from the stack. For the add, you just put an element to the second.
I'm sorry, I just cannot get how it is connected with the maximum. Like, I understand the algorithm, but I cannot understand how it is like purpose to find the maximum of the key.
It will be pretty simple. But like, is it clear? Like, the question is it clear how to emulate Q with two stacks?
Yes.
Yeah.
Konstantin, is it clear? It was clear?
Yes.
Okay, good. So how to answer the maximum? What is the maximum of the stack? Do you want to think a little bit, or should I reveal? Okay, let's think like for 1 minute, and then if you don't come up, I will explain it anyway. Like the function is really simple. If we allow that stack has three operations: push, pop, and max. As we already told last time, we know how to implement stack with maximum, so we can have the stack with an operation max on it. Come on, it's simple.
So we need first stack where maximum value.
Not exactly, but it becomes warmer. Please note that you do not have any unnecessary elements in the first and the second stack. All the elements that are in the queue, they lie in F and S. it seems that like I did again something wrong, because like it's pretty simple and like you cannot get that's very strange. Then it seems I explained something not very simple. So like I just try to return max f dot max and s dot max. So since all the elements align in f and s, and there is no other elements there, so we can take the maximum in the first step, then we can take the maximum in the second step, and take the maximum out of these two values. This will give you the maximum in the stack, or in the queue in general.
Oh, okay, it was very simple.
Yeah, it was very simple. So like, I don't understand why you didn't come up with this.
I think we need to realize maximum of the stack also. And
Yeah, I wrote it. I wrote it here. So push pop max.
okay.
So I gave you this maximum operation here.
Okay.
Yeah. So like when you have the stack with this maximum operation, everything becomes much clearer, right?
Yes.
Okay. So that is right now everything that I wanted to talk with you about Q. I mean, this is very funny thing on how to emulate their Q using stacks. It is very important for my sense because it's quite cute. So right now we will talk a little bit about more powerful data structure, but we will not talk a lot about it. So there is DAG data structure. DAG data structure supports 4 operations. Push first, pop first, push last, pop last. So it simply can put at the, like, it's kind of queue, but it can only pop from their beginning, and it can add at the beginning and pop from the end. So push first adds to the beginning of their data structure, pop takes the first element from the data structure, push last add at the back of the data structure, and pop last is to take the last element out. So like there are 2 questions for you at the same time, like which you should answer very simply. So suppose you are given DAC. How to implement stack and how to implement queue. So you are given this data structure with these 4 operations. How to implement queue using that and how to implement stack.
We shall use necessary method. It's going to stack. It's going to be pop last. Yes, pop first from the head, and also push to the head.
Okay, good.
And for the queue, it's going to be we're waiting push to the last and pop first.
Yeah, exactly. Does everybody understand that?
Yeah.
Okay, great. So is it clear how to implement it using two counters as tail and head? Like, is there somebody who are not sure in himself and don't understand how to write? how to write it using like two counters, left and right, where you just, when you pop from the top, you just increase the left. When you push to the left, you decrease left, and the same on the right happening. So I wanted to tell you that there is, so for the queue, there in Java there is queue integer integer. Oh, sorry, you don't need this. And there is array DAC with integer here, q DAC. The D equals new array DAC. So these are data structures that are implemented in Java. So you can simply use them in any problems you want. Yeah, but obviously the thing with two stacks you have to implement kind of on your own. But you can use stack. You can use stack data structure there, as we discussed the last time. So let us come to the next data structure, which is also important. I will take the thing on how to implement the stack later. So we will talk about how to implement stack if we will have time. I hope that we will have a little bit of time, but because it's kind of complicated. How to implement stack without taking whole memory at the beginning, like to not allocate array. I will take it to the next lecture if so. So, oh no, let me think a little bit. No, let's talk about this next time. So we will talk about heap. So what is heap? Heap is a priority queue. Is an implementation of the priority queue. And priority queue has two operations: add x and extract minimum. So we can add an element into the heap and take their smallest element out of that. I will explain you how to do this in of logarithm and time per each. The algorithm is pretty simple. So you build a full binary tree. With the following condition, that the parent contains an element that is smaller than both children. So like we have this inequalities per each node. So now everybody understands how to implement get minimum, not to extract, but simply get.
Yeah, we should just follow the left, like go down, 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 down.
No, you just return the root. The root is the minimal one, so you can see.
Yeah, so, yeah, got it. Yeah, the opposite one, yeah.
Okay, so how is typical this data structure is implemented? So we maintain this everything in the array. So we have this is 0th elements, this is 1st, 2nd, 3rd, 4th, 6th, 5th, 6th and 7th, 8th, 9th, 10th, 11th. So let us become clear from the first. So if this element is I, then its children are 2i plus 1 and 2i plus 2. So like, yeah, this is represented as the array. So 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So you can see that the children of the node I are 2i plus 1 and 2i plus 2. And the parent of an element I is I minus 1 over 2 with their floor I minus 1 over 2. So you can take, for example, 4 minus 1 over 2, will be 3 over 2, 3 over 2 is 1, so on, etc. So the heap is managed as their the prefix of the array. So like here it can be 12, 14, 13, and etc. So how to add the new element? So we want to get the 12. We want to insert the new element. So we know that the current size is 11. Then we increase the size to the 12 and put an element at the position 12. So you kind of add this node here and you take x here. What should we do? So you can see that the fifth guy and x do not necessarily satisfy our condition that each parent is less than its children. So what should we do in this case? Do you have any ideas?
We need to compare it to the parent and push it upper if it's less than parent.
Is it like happify thing?
Yeah,
And,
it's the
if it's less than parent, so we keep it on this way.
Yeah, exactly. So you just take x and try to go upwards. If it is less than parent, then we swap it with the parent. Then if it's again less than the parent, then we go up, and etc. So the operation is pretty simple. So you have add x, you have a heap of size plus plus equals to x, and we have a node v which is equal to size minus 1, and then while v bigger than 0, you just if heap of v minus 1 over 2 bigger than heap of v, then swap heap v minus 1, 2 heap v, else break. Oh, yeah, and we have v set to v minus 1 over 2. So what's happening here? We add the element to the end of the heap, then we go by parents, so we take we are going higher, and if we are smaller than the parent, then we swap to element, otherwise we should stop, so everything is everything is okay with our data structure. Is it clear? Is it clear? So like this operation is named shift up. So then we want to make extract minimum. So here is the simplest way on how to do it. We just take the answer as answer equals to heap of 0. Like this is the value that is stored in the 0. And then we should get rid of this one. So you just say that heap 0 is equal to heap minus minus size. So you just swap, you just take the place of the latest element in the heap. So you just take 11 out of here and place the value that was at 11 here. Then we should like update the data structure in such a manner that it will maintain the same invariance. So we have these three guys. Who should we place in the root? So we know that the first guy maintains the smallest element in this subtree, and the second guy maintains the smallest element in this subtree. So whom we should place at the root right now?
Smallest of 0 and 2.
To be more precise, we should take minimum from this one, and this one, from 3. So from both children, because some of this, like we don't know the relation between 1 and 2. So we know that the first is the best in the left subtree, second is the best in the right subtree, and probably this guy is the best. We don't know. Yeah.
We need to compare it with first and second, and put to the root that leaf who will be smaller.
Yeah. So what's happened? Suppose that we get second here. So we know that this one is the smallest in the tree. What we're doing next? You can see that this edge is already satisfied by the condition because V2 is the smallest element in the whole tree. So what's happening next here?
Compare it again.
Yeah. We again compare against two children and so on. So while we say that v equals to 0, u equals to v if 2v plus 1, heap 2v plus 1 less than heap of v, then u equals to v plus 1 if h 2v plus 2 less than h u, then u equals to v plus 2. If v is equal to u, then break. Otherwise swap h u with hv. And finally, what we are going to do, we are going to set v to u. So here is, in this place, we will find u, which is the smallest one. Which out of the three nodes the smallest. Then we swap them between each and continue with their children. Or if we are the best, then we stop in this place. So what is the condition here? What should be the condition? When we should stop?
If there is no children left,
Yeah, if there is no children left, what is the condition there?
that's 2b plus 2 equal or more than size. So it will just more than size.
Okay, almost perfect. I would say that here is 1 because we will have. Yeah. So you were right. Sorry, yeah, it was less than equal. So yeah, it was okay previously. Yeah. So and here we should add additional condition that 2b plus 2 less than size. That's all. This means that at least one children is in the heap. Yeah. Thank you, Elizaveta. So, is it clear how to write heap sort? How to make a sort algorithm out of that?
Yeah, kind of, yeah.
What?
If you asked, is it clear? Yes, it is clear.
Yes, it is clear. Okay, good. So there will be a little bit more complicated problem in their homework, but I insist you to do this. Suppose that we add additional operation. Oh yeah, sorry. Why it is logarithm n? Is it clear? Why both operations perform in logarithm n?
Because we only have like the half of.
Because the height of this whole thing is
log of n.
log n, yeah, and each operation works not worse than the height itself. So suppose that we add another operation as decrease key x. So how would you perform this?
May I ask what does that mean, decrease key?
Oh, decrease key, sorry. Decrease key. Okay, so you take an element x and you decrease its value by k.
Firstly, we should find it, then we should decrease it, and then we should rebalance.
Yeah, how to rebalance?
Same stuff when we compare, we go and shift up.
Okay, yeah. So we do shift up, so we decrease an element and then shift up. Yeah, by the way, this guy is named shift down. Surprisingly. Okay. Okay, is heap clear for you? If it is clear, let's come to. We have 20 minutes approximately, so we will talk about the vector how to implement vector on, or to be more precise, how to implement stack with no additional memory, typically. So the problem with the stack was that push operation so it makes so in the push operation you add an element at the back or at the top. So the question is, suppose we don't know their total size of the queue of the stack, like we don't know the maximal size of the stack. The question is how to alleviate this problem by saving the complexity of the data structure, or to be more precise, of one time. So let us do the following. If size is equals to capacity, so capacity is the length of the array, then we will do the following. We will take a new array A. We take new int, I don't know, like new int with two times capacity. 2 times capacity. Then you copy from stack to A the length of C, and then you tell the stack equals to A, and then you tell A top plus plus equals to X. So when we are out of bounds, then we create an array of 2 times bigger. We copy everything from the stack and they make stack as this array. So we have 2 times more additional memory. Why I chose here 2 times C? Why not C plus 1, for example? Unfortunately, if you do C plus 1, you will copy the data structure almost on each push. So it is not very good. And here I can tell that amortized time of their operation will be constant. What is amortization? So we have a bunch of operations. Okay. And each operation has its own time of OI. We tell that we have an amortized time of the operation TOI. Is that sum of TOI less than sum of T amortized with operation? So let me give you a very short, right now, a very short, straightforward proof of why push works in constant amortized time. So when you add push 1, you create a new array and you add 1 here. Like you copy the size of 1. Then when you add the second element, you again create the new array and add 2. So like this one is push, this one is copy. Sorry, this one is push, this one is copy. Like this was the first, this was push 1, this was push 2. So, do we have to copy when we get the third element?
No, the length of array is 4.
Yeah, the length is 4, so we take the next element 4 and we add, how much do we add? So this was push 3 and this is push 4. No, we have 4. We have 4 elements and we increase its size 2 times, so we get 8. And we copy 4 elements there. So, and etc. So finally, I don't know, push 2 times k, which will be plus 1 plus 2 in the power of k. So if we calculate this properly, so we have 2 in the power of k push operations. This was on push. And 1 plus 2 plus 4 plus etc. plus 2k, which are the total number of copying. So this will be in total 2k. And what this sum is, do you remember? What this sum is equals to?
Arithmetic progression, but
yeah, it's arithmetic progression, that's right. You should be able to do on the fly. Okay, let me repeat. So it is 2k plus 1 minus 1. So it is the next power of 2 minus 1. So this is, to be more precise, 3 times 2k minus 1. Where 2k is kind of n, the total number of operations. So if we take TOI as 3, then we'll be fine. So the amortization time in this place is constant, and to be more precise, kind of it is 3. Because this is less than 3 times n. So this is a straightforward proof. It's very hard to prove using the straightforward idea. Instead of that, let's do this through bank accounting idea. What is the bank accounting idea? So when you perform an operation, you could put several coins on their positions in the array. And when you perform an operation, you can take the coins that are already there. So you kind of spend the coin that you left for you before. So suppose that we just doubled the array. So it's here. The stack right now is here. So when we make push, let us put 2 coins. We will put 1 coin here and 1 coin here. Then when we add the next element, we put 1 coin here and 1 coin here. So each operation costs the normal amount of time that it costs in general, plus the total number of coins. Here we put 2 coins per operation, so their operation time is 3. Then we put again like coin here, and etc. until we get to the end where we put coin, another coin, and then we are coming to increase the size of the array. So for that we increase the size of the array 2 times, and then we see we have each element with a coin on it. So we have an additional linear time that we can spend, and we can spend each coin on copying it to the new array. You just copy all the elements there. So you just put 2 coins per operation for the future thing, and then you can operate their copying process in 0 time for you, in 0 number of coins for you. Okay. Is it clear? So this thing is named amortized time. So this. When we talk about amortized time, this is like how we amortize the total time over all their operations. Is the coins idea clear in this example? If there are any questions, let's talk about them.
Could you please explain one more time?
Okay, yeah, sure. So, what is the idea of coins? We again, with the operation, when we perform an operation, we can put additional coins, like spend the time to the future. So you can put a coin, you like pay 1 coin in advance. So suppose that we have a new array which have only half of elements, and then you make a lot of push operations. So when you make a push, we want to spend our coins in the future on the copying part. So before we make copy, we want to have each cell to have a coin to copy. So we can pay 1 coin to copy here. So then when we make a push, we put copy in the cell where you push an array, push an element, and to the element which corresponds to the capacity minus capacity over 2. Then when you add with the push the element at the position I, you put a coin at position I and at the position I minus C over 2, where C is the capacity. You can also have pop operations there, which, for example, like you put 2 coins, then you make a pop operation, and then you add, like, perform again the push operation here, then you save 2 coins here. But we will be needed only 1. So and so on. When you push an element to the position I, you add a coin at the position I minus C over 2. So when you get out of the bounds, each element here have a coin. Then we can spend this coin to copy it from one array to another array. So like this coin kind of gives us one additional operation in the future. Does it become clear?
So we have some reservation of time in the future for our operation, and coins represent this time in the future.
Yeah. These coins represent the time in the future. Yeah. It is not trivial, this bank accounting thing, but it is the simplest thing with the amortized time proofs. So for example, it will be enough here not like 2 times c, but like any value which is higher than 1.0 here as the multiplier. Anything should be enough for us to be more precise. So what's with the time? Okay. One more thing is so this is how array list works in Java. So like there is array list, and the array def also. So array list. You just can add an element to the end, and it will work in a similar manner. So it works as adding an element and looks at the size of it. If the size is not enough, then we increase it 2 times more. Okay. One more thing. Let's talk about potentials. I will take a little bit of time from you. So each operation, each amortized time right now will be equal to time per operation itself plus the potential minus the previous potential. So each state of our data structure will have a potential there. So it has, like, in our case, for example, push operation is 1, costs 1, but like, and then we talk about their potential itself. So we would think that potentials itself, for the simplicity right now, that it is bigger than 0, and the potential at the beginning is 0 itself. So when you add all this t here, so you have some t of I, which is amortized, which is equal to some t of I plus phi of I minus phi I minus 1, and it at the same time, if you calculate it properly, it will be equal to plus phi of n minus phi of 0. So all these potentials will cancel each other out, except for the last one and except for the first one, which should be bigger than t o I, because phi of 0 is 0, and this one is bigger than 0 by our condition. So then the question is how to get the potential that kind of cancels very long operations. The first, so you have this array here, and you suppose that you get this part where you copy everything. So it is TOI plus potential previous potential minus previous potential. So the operation itself costs our capacity. This capacity. This is 2 capacity. So it costs us capacity time. And however, we want it to be of 1. So our new potential should be small. So yeah, so since you want to have it as O of 1, this difference in potential should be approximately minus C. So this means that potential of the previous state is much higher than the potential of the current state. Let's consider the potential as the number of elements that are coming to the right part. So here is like that, and the potential of the state will be like this. For our new state, there is no elements here, so our potential will be equal to 0. At the same time, for this array, the potential was equal to this number of elements. And if we multiply this by 2, we will get that you get from then your potential for the previous state will be C, and potential of the current state is 0. So you will get exactly minus C here, and you will have O of constant time. I know that it's hard to understand right now, but like, did you understand at least something from this thing?
Well, something, yes. Not the whole thing, but okay.
Yeah, I mean, you can do it at home. Like I can tell you that their potential should be 2 times the number of elements minus capacity. So in this case, it will be 2 times the number of elements C. There is C elements here, minus the capacity of this array, which is C, which in total will give you S. And this one, it has the number of elements as C, 2 times C, and capacity right now is 2C also, so like the potential here is 0. So I gave you the potential, and if you have time at home and you want to understand this is better, then you just take this potential and put it inside here. So you like take the operation, how much it costs itself, plus the difference between the potentials. It will appear that their amortized time will be constant. It will be, to be more precise, it should be approximately 3 there. Okay. Do you have any questions for today's lecture?
No.
Okay, good.
Maybe you know some articles about this subject.
Yeah, typically you can read everything in Russian at. There is a very good site with their Wikipedia there. So on the amortized time you can find it. So neerc.ifmo.ru/wiki.
Okay, thank you.
And there is a Wikipedia on the, not on the whole thing that I'm talking about, like, but on most On most things there is everything written there. Okay, then we finish for today. Thank you very much for coming. See you next week.
Thank you very much.